Hello, everyone. Welcome back to the AAS YouTube channel. And this one's going to go down in the AAS Author Series. And today we're going to cover a seminal paper. And I'm so happy to have the lead author of that paper, Kris Górski, with us today. Hey, Kris.
Hello. Hi, Frank.
How you doing?
I'm all right. And you?
I love those pictures behind you. Look like we have some Polish stamps there.
Yep. The Vienna victory from 17th century. So anyway, yep, that was a commemorative stamp.
Yeah, very good.
Venice on the other side. What a combination.
Very good. Where are you at these days? Where are you working at?
Well, I'm still at JPL as when the paper came out. I've been here in Pasadena since 2003. Pretty much covered the main part of operations of the Planck mission through the end.
Okay.
That is actually still ending, as the last round of papers didn't yet come out. They are almost ready. I believe there is only one or two that are in the final brush-up stage with astronomy and astrophysics, and then I suppose they will do a dedicated volume on that as well. So this was 2018 to appear 2020. That will be the final publication output of Planck. And I'm in transition stage to the future post-Planck, kind of working on a bunch of things at JPL. Still some in cosmology and thinking about CMB in the future, going towards probe mission concepts and so forth, and also sinking teeth and some other things. Actually through Heelpicks to talk to some colleagues in Earth observing and also doing some planetary science work with modeling gravity fields and stuff like that on planets. So quite a few things. It's a big lab, huge number of people, cool. Large portfolio. So if you're curious, you always find something interesting.
Very cool. All right, so let's get to it. And before we get started on Heelpicks, I want to motivate a little bit why I chose this paper. As some of you know, I have a research interest in the evolution of the most cited astronomy and astrophysics papers and their journals. So this paper was published in 2005, and in the big, bold red line there is the paper we're going to talk about, Heelpicks. And so it started out at the end of 2005, a little bit below one of the top 50, but then it climbed very quickly into the top 10 after about 2-3 years. And ever since then, since about 2007 or so, it's certainly been a top 10 paper, currently sitting at number 6 as defined by how astronomy papers are defined in the method used. And so that's why I want to talk about it, because it's a seminal paper. I will tell you as an editor for the AAS journals, over and over again, you see software citations / software, use it, to Heelpicks. So let's go ahead and talk about Heelpicks, a framework for high resolution discretization and fast analysis of data distributed on the sphere. And Kris, take it away.
Thank you. Well, it's a bit of an old story, and there is the meat of the paper itself and the actual mathematical method and the software library we built and supported ever since. But there is the part of motivation and human story behind it that's not carried through the journal article itself. So I will allow myself to have a few words on that.
Please do.
Paper was put through publication in 2005. The actual work started around end of 2006, mostly in 1996 and 1997, when I was in Copenhagen at the Theoretical Astrophysics Center. Okay. After a few years that I spent on COBE. So this whole thing emerged from gaining experience with working on CMB data in the form of maps and then spectra and other things derived for characterization of science that it informed us on, and understanding what were the needs that were brought about because of quick transition towards what later became the WMAP project and a little later Planck, where the whole regime of understanding what mapping the sky meant changed rather drastically in a short time. If we remind ourselves the maps of CMB anisotropy generated from the data from COBE gave us 6,000 pixels on the sky, so oversampling the beam resolution, so about 1,000 points on the sky to do science with. And that we dealt with a completely different generation of computer hardware. I had an Alpha Deck workstation at Goddard I worked with.
Yes, I remember those.
From today's perspective, pretty much hands-on. And then legacy of COBE was a software and the type of thinking about how you approach these problems. So I remember very vividly that as it naturally goes, the legacy of COBE got people interested in modeling what was necessary to be modeled for WMAP and later Planck was attempted initially with software inherited from COBE, and it simply ran very slow and seemed hopeless. And therefore I started thinking about the geometrical aspects of it. What does it mean to organize data on the sphere in a way that would support the type of analysis that would allow us comfortably to do drastic increase of angular resolution in the data and handle it in a comfortable time. So that's how Heelpix emerged. So it took a few months of thinking about geometry, quite obsessive. Then Eric Yvon, who's a massive pillar of this work as well, until today, was a postdoc who started working with me. Vandelt came along, he was also a postdoc. Tony Bande was a colleague from COBE, who at that time was in Munich. We worked together a lot. Hansen came along as a student and contributes somewhat. Martin Reinecke came later on. Until today, he contributes massively to various aspects of advanced software development on this. And then Matthias Bartelmann was then still in Munich and also helped with it. That was the group of people who agglomerated on this paper.
Cool.
So now going on to the idea, it was clear that you have to define funny pixels on the sphere, because you cannot, unfortunately, do the sphere in terms of tiling with squares or rectangles or anything like that because of curvature. There were, of course, many attempts to do that before. Particular one that was deployed on COBE and was quite popular in usage in various NASA datasets was called hierarchical quadrilateral sphere partition, quad cube. For short, it was an example of a noble line of work of partitioning the sphere, starting from classical volume selections like cube or icosahedron inscribed in a sphere, partitioned in a certain way, projected onto a sphere to generate elements to your desire, perhaps equal area or otherwise. And all of these shared properties that were undesirable in a sense that they didn't dialogue very well with what's required for spherical harmonic analysis, which is the carrier of most of the analysis of the type that we did in CMB.
Right.
And that's for the reason of the functions that we use being factorized between longitude and latitude, if you will. And all of these geometric partitions that were commonly used did it in such a way that they oversampled on latitude in terms of what was the requirement of computation of the functions that would be used in the analysis. So it was clear to me that you have to change it, go to something that would be in between geographic grid, which is isolatitude,
right,
as a single point in latitude and many points in theta that saves time in calculation, but also change geometrically, because by that time I took in the load of literature, mostly in geophysics, where a lot of people would do a lot, and until today do a lot of work in this so-called either equal coordinate partition or geographic grid, constant theta, delta theta, constant delta phi, always complaining about massive oversampling mathematically with pixels around the poles, both being singular points mathematically, but also then not corresponding very well to natural instrument resolution. Typically you measure on the full sky or on the surface of the earth with the same resolution wherever you look. But mathematics was structured differently. So I said, yeah, okay, you have to drop that and do something about it. And progressively over time, we came up with a set of what we call requirements on the next page for what would be more effective way of doing this. which would be one that you would ideally like to have equal area pixels to sample the full surface of the sphere. You would like them isolatitudinally distributed. And then for computations, you want to number them and have effective numbering scheme that would help with some aspects of computerized work with such structure of the data.
Right.
And eventually Heelpix was born out of it. Maybe you should go to figure 1 indeed, a little figure 2 actually.
Figure 2.
Figure 2.
Awesome.
Or even figure 3. Actually, the figure, sorry, it's a figure 3. This is the one that was most often copied. This is Heelpix specific in terms of the construction that we eventually put in the software, and that mostly is used in applications. So here you see all the elements of Heelpix visually on the sphere, encapsulated, right? So you have a hierarchical partition going from top left clockwise, starting with 12 big tiles, 2 of which are colored in different shade of gray. They're complex in shape, they are quadrilateral, they are actually equal area. And then you can find a way, this was the whole point of it, of curvilinearly partitioning them in 2 by 2 slice to generate next order partition with 4 identically sized pixels fitting exactly in the mother pixel and follow ad infinitum. So this is what Heelpix is. If you look at the distribution of black dots as pixel centers, so to speak, you will hopefully see that they are isolatitude. All of them lie at any given resolution on rings of constant latitude.
Right.
And we'll show elsewhere what the indexation aspects are, okay? So this turned out geometrically, algebraically extremely effective and successful for several reasons. We came up with what I won't go through, it's in the paper. You can see it partially to the right, the beginning of description of it. The description of how angular coordinates translate into indexes of pixels and so forth, and how you compute boundaries, all of that is analytical and explicit in a sense of parametrization of angular resolution, okay? So when you say that you want some very high resolution multi-million pixel construct generated out of this by cascading down to smaller and smaller pixels, as we needed for Planck eventually. We worked with maps mostly at 50 million pixel resolution on the sky, sometimes 200 million.
Okay, cool.
The parameter inside, which is number of pixels along the edge of each such quadrilateral shown, big quadrilateral from 0 order partition, it explicitly characterizes algebraic description of everything from that point on. And I stress this point because there are beautiful mathematical constructions otherwise, which go through a different construct, more kind of dynamic mathematically, involving recursive calculation. You can build geometric model of sphere partition, starting with triangular partition and then subdividing triangles into 4 triangles and so forth and so on. And you'll have this cascading hierarchical division at hand. And it's recursively evaluated, meaning that if you want to go to sub-arc millionth of arc second resolution, you have to start at low resolution and keep computing. So each time you call something between angular coordinates and indices, you will compute a lot on the way, and it accumulates, produces a hit in the end in performance. Heelpix is explicit, it always computes at the resolution of interest. So that's just as a computing aspect goes on that. So now if we go back to figure 2, this shows a bunch of partitions of the sphere, which are parameterized roughly by the number of layers going pole to pole and the number of pixels going around equator or in latitude, longitude. And Heelpix, the one we just looked at, is the middle one on the right side. 3 and 4 are the numbers of partitions, pole to pole and longitudinally. You can do it differently and work with it if you please. So, you know, all of that, each one of them is characterized by the same algebra. with these parameters n theta and phi, defining how you do that. And effectively, this also illustrates graphically that basically we came up with a scheme of sphere partition that's mathematical and unique, as it didn't exist before as a proposal for dealing with what some people refer to as flattening of the sphere or flattening of the Earth. It's a famous book by Snyder on cartography.
Yep.
It's called Flattening of the Earth.
Yep.
There are approaches to this in this field to building mathematical constructs like that ab initio from equations that define the properties of projections from the sphere to the plane. We didn't do it that way. We were much more pedestrian. We kind of constructed it by sheer force of will and perseverance, and then build up algebra and analytics around it. And then it all met in other people pointing out to us that that actually is an effective mathematical merger of two previously known spherical projections, one that works in Heelpicks in polar regions and the other in equatorial region, analytically merged at intermediate elevations, which nobody proposed before. Therefore, in that sense, it's an original cartographic projection as it emerged, and some people acknowledge that. So that's pretty cute. Cool. And if we go back to figure 1, this illustrates the nature of advantages of hierarchical partition. If you can arrange your pixels in something that projects into squares, and then you can binarily label them. So you have 0, 1, 2, 3 pixel indices and their binary representation underneath. And then all of that one step up to one higher degree of resolution. It illustrates, if you follow for a moment, what happens with the bits binary representation at the bottom of each tile, that the bits on the left are forward segments of the binary representation of the higher resolution bits. So retaining binary representation allows you very quick manipulation of resolution of the maps by trimming the bit representation of the pixel index in that arrangement, okay? Right. And that maps onto Heelpicks for the reasons that we will now move on and show. Let's scroll down to some other figures. So since Heelpicks is called hierarchical, that is embedded in it. And next, further on, pixel indexation, here, that one, the 4 things. Heelpicks pixels can be numbered into, the figure number 4 it was, I think, please. Sorry? Yeah, this one. So it has a stack of 4 pictures in 2 different indexation schemes, because the trivial one simply runs from pole to pole. This is the one on the top, and the third one down, the higher resolution of it. So it simply numbers them on each rings and winds down. Trivial and useful for simple calculations. And then the indexed one shows you the same pixels labeled in the different scheme. So you see how the numbers are running differently. And each of these quadrilaterals that you see here, better in equatorial range, illustrates what was shown on the previous figure, the nested run of pixel numbers that underneath permits that binary representation and manipulation thereof. So that nested scheme and hierarchical representation of the discretization is useful. Historically, it was important, and that's why QuadCube had that property, and it was desired and requested by NASA to be inbuilt in it when they commissioned creation of QuadCube mathematics for them and software. Okay. Because at that time with computing devices, of course, everything was linear storage. When you had a large data set at the time, that was just a single string of numbers, which if you didn't carefully preconceive have these numbers represented where you are on the domain, on the sphere in this case, you could have physically very nearby elements separated by very large distance on the storage device. And when you did it in the database or on disk or tape or whatever, to read the data and start looking for neighbors, you would have to run the reader all the time over the whole data volume, wasting enormous amount of time. Right. And hierarchical scheme was a partial answer to obviating that problem, because in large areas on a sphere, in this case, all these nested pixels are nested together close by. Right. And then they would sit as indices on the storage device close together as well. So that would be the element that would bring import the speed of computation, and in various area searches on the domain that would be very loaded, extended, had to be run repetitively, and would require dynamic interaction with indexing of the data object versus physical domain coordinates, okay? That's why we put hierarchicity on it. Okay, and then we can move on, please. Isolatitude in the end. Okay, let's stop on table 1. That's just the simple enumeration of resolution and couple of representation. Our param. Oh, sorry about that.
All good.
Suffered the realism.
Brought to you live.
Yeah. So inside is power of 2 number. That's the number of pixels along the edge of the large 0 resolution pixel. If you scroll down to numbers like 2048, 4096, and 1024, these were the resolutions with which we worked on Planck. WMAP released most data on 512. So you see it's mapping to between 3 million and 200 million pixels, and angular resolution of them, characteristic for the field of CMB is given in the right column. You can go ad infinitum with it as much as you have enough storage to actually put the map down, and CPU to load it as a single object, for example, on your computer. The largest I went through so far on the machines I have in my personal domain was inside 16,000 calculation. When I messed around with a little bit of Earth topography data. Intrinsically, Heelpix software has been built with some limitations to 8,192 on some objects that are required for CMB analysis. But these are specious secondary limitations that are irrelevant from pure mathematical point of view. You can use construction like that to discretize to arbitrary resolution, modulo the availability of computing resources.
Yep.
Then we can scroll down and show the, this was projection, doesn't matter. Let's just go with here. I mentioned briefly these Platonic solid constructs. So on top we have quad cube, which is a projection on the sphere from the cube inscribed in that sphere, and icosahedron, same thing for icosahedron inscribed.
Right.
If you put those points around, you can compute the boundaries in a certain way and so forth. You have a pixelization. And the shaded region shows you the smallest number of elements of these pixels for which you would have to explicitly compute the values of associated Legendre polynomials in order to carry numerical version of spherical harmonic analysis. So the point of that plot is that that domain on quad cube and icosahedron is 2-dimensional. And when you go to equal coordinate partition below, or geographic grid, or Heelpix, you have a 1-dimensional slice of through pixels for which you have to compute PLM as associated Legendre polynomials to do all spherical harmonic analysis. So there is dimensionality difference in terms of how much you have to cover. So now if you now imagine upgrading this to very high resolution, the scaling is different with number of pixels, and that's illustrated on the top of the plot of the page, that in terms of evaluating a global power spectrum on the whole sphere, or spherical harmonic transform, and you scale that with the number of pixels over which you run, you vary by square root of number of pixels in the speed attained on that primitive differentiation between different type of constructs. And that's a very significant speed difference when you get to millions of pixels. That's why, as I mentioned already, early attempts at modeling WMAP, even at resolution smaller than what WMAP eventually used for the data, resulted in calculations which shocked people, because they took constructs like this quad cube on the left side, ran power spectra analysis codes with them on simulated maps, and then it was running for weeks on workstations at the time, while the first time we put Heelpix together, we just got performance of some small number of minutes. And present computers with you know, number of cores available, some simple elements of parallelization, and we do spherical harmonic transforms on data sizes of Planck in a matter of seconds. It's just
It's amazing.
crazy.
Yeah.
So that was the essence of it. That's why it took seed. So, you know, when I put it together, like I said, I started working on it effectively 97, 98 was when it was formulated, wasn't yet an effective software package, was more an idea with some elements of software attached to it. We had discussions between ourselves. What the hell are we going to do with all of that? Arguments were made. We need to talk to people who will be consumers. So I visited my friends at Goddard, presented it to them. Well, of all people in the world, they were the ones most quickly to understand that it was useful. So they committed to taking it under condition that we make a software package out of it and it's usable to people who would like access to WMAP data. So that's what put us on the path of building the library and releasing it. And it was in operation for several years before this paper appeared. So we had this kind of research and development work with feedback from people going on for a while before this paper then encapsulated how it sort of firmed up. But then I moved to European Southern Observatory and it ran from Munich for 3 years. And then I moved back to Pasadena, and in 2003 it found foothold at JPL, and at that time Planck committed to using it. And you know, I have to say what you stated, the citation numbers and so forth, all of that is a reflection that eventually it transcended the CMB usage. In CMB, it became ubiquitous, and a lot of simulation work until today is carried on that. And of course, we have two legacy data sets now, WMAP and Planck, that have usage, and all of that is encapsulated in Heelpicks. So that drives the use. But it has been used by Fermi-Lat for representing gamma ray sky. It's been used by a number of ground-based experiments for various applications. It's been used to render radio data, X-ray data, and so forth and so on. So I can't complain. As diffuse data goes and very large area or full sky data goes, I think its importance is recognized. Even though those many years ago, so almost more than 20 years ago, when I started getting into this and arguing that that might be a really effective way of going forward with standardization of rendition of data and some elements of its analysis, oftentimes would I be met with skepticism and statements that why the hell would we do this when it looks so weird? Maybe something better will come along. And I say, okay, well, let's wait until something better comes along. And I'm still waiting. So, of course, there are constructs that are pondered here and there. There are expansions on the Heelpix concept and stuff, but I think it defended itself real well, and that's the result of it is the statistics that you presented. So that's where we are.
Cool. So just to push on the future a little bit, you mentioned a little bit, but do you ever envision a Heelpix 2.0, a Heelpix 3.0?
Well, it is already, I think, 3 point something in terms of software upgrades. Well, I mean, so that takes us over from kind of mathematical geometric thinking to practicalities of software management. Wasn't my forte, that's not my professional area, but I've got help from these postdocs and colleagues and stuff and others. And we always envisioned that if there is a usage base growing, we were open to people feeding back and interacting and helping grow the library. That worked to some extent. It didn't really overwhelm what our development was. What our original plan was to provide support in several languages. I mean, the software in several languages to have equivalent functions executable either in Fortran, which originally was used to write it. Now there is a parallel C++ library and so forth. And then we started the visualization and kind of data interactive work support through IDL. Software right now, it kind of morphs more into Python, and have people who joined and copied some of these utilities to Python, first under the umbrella of Planck collaboration. Now it sort of lives alone, but it's still distributed as primary source together with Heelpix library. So, and then we upgrade once, twice a year. We collect bug reports, and we always welcome feedback. And if anybody builds an application they think can change the world and is Heelpix rooted, we'll take it, we'll distribute it, we'll acknowledge it. Otherwise, people wrote libraries, for example, of wavelet analysis on the sphere that at the root underneath run on Heelpix. And that's fine. They live separately. They acknowledge that. So all of that is meshing in the most weird way, which I slowly stop following because it's got its own life that way. So what the future brings in terms of concept, I think that the geometric concept of Heelpix is solid. A package of more effective or slightly differently oriented analysis tools can grow, and some of that we try to build. With every release there are some routines added here and there based on experience we're acquiring, and well, the boost for our own work probably will come with more demanding research front to be revisited. So one such research front will be whenever we live long enough to see full sky high resolution polarization mapping, to see if Heelpix supports scalar functions and tensor functions and vector functions in the sphere. So of course it does support Planck polarization analysis rendered in Heelpix and so forth, but the higher resolution you go, the more meat you have to grind and so forth. At some point, mathematical issues arise. So Heelpix itself as mathematical concept is not a pure mathematics construct as like, I don't know, Euclidean axioms or something, because this is an unpleasant part of life, that the geometry of the sphere doesn't support perfect geometric slicing like a plane or a line. And you cut corners here and there, and then spherical harmonic analysis also is approximate, because it's always approximate when it's discretized, but there is a degree of accuracy that you have to ponder at some point. So in CMB area, data are noisy, and we very carefully always followed the tracing of how accurate it is in calculation intrinsically versus where the noise levels are, and doesn't compromise it.
Right.
If you would like to use Heelpix as a mathematical type quadrature on the sphere, you have to be extra careful, because it is not that, and it creates errors in representation of discrete representation of integrals, and you have to be so there are we have ongoing discussions to some extent with people who of course argue, no, you should do something like Gauss-Legendre quadrature and this, that, and the other on theta, which is correct from mathematic purist point of view. Unfortunately, it doesn't couple to effective scalable and hierarchical geometric partition on the sphere. So you're always hit somewhere and you make compromises. And I think Heelpix was an excellent compromise. It lived a long life. I think it has a life ahead of itself. And I think it has a life potentially as a standardization tool for a variety of data over large areas of the sky, where you could do what we did with Planck and WMAP. We could analyze these two data sets thanks to being represented the same way immediately without even thinking about it.
There you go.
They were just the same thing, one-to-one compare. And if you can import, like I said, gamma ray, radio, and all of that, X-ray into this, that helps life a lot. So yes, at the initial price of accepting slightly more complicated than square grid of points partition, which comes with software that lets you handle it, you don't even really have to resolve anything yourself, then you get tremendous benefits and you help a lot of data analysis downstream.
Sure.
So that's the future. As long as we live, we'll see. I mean, I'm trying to, like I said, step outside of astronomy proper, talk to Earth observing people a little bit in planetary science at JPL. Some of that may lead to opening it up to other disciplines, see how that gets going, and ultimately it's all about support. So, of course, I've been lucky to be supported for a long time by a big project. Planck helped make it live. Right now we are a dispersed group. Most of my colleagues are in Europe, actually. and whether this has a chance to become a project that will have further life as I don't know, let's get a student or a postdoc and ponder some other visualization that's more modernized or whatever. I ponder all of these things. I would like to do that. It will depend on the possibility of creating some kind of modest funding stream for it, which we're trying to work on. So we'll see.
It's always a good challenge with software projects.
Absolutely, absolutely. The whole philosophy of that is upside down.
Boy, we could go on. We could talk about that one for a long time. Believe me.
I'm sorry, so you don't have to edit that out.
No. Believe me, I'm well versed in the challenges of community-driven software.
Right.
So,
although the recognition of importance of it seems to be growing, because even without my participation, I do hear colleagues reporting that both at IAU meetings and AAS meetings, they are now beginning to create interest groups, finally recognize. I was told that, 30 years ago that CMB was an ideal field to ponder what's with people who are not pure theorists versus pure instrument builders in astronomy. There are people in between who actually, if you think about it, carry most of the science analysis of these data sets, but they're not pure. So traditional academic thinking about it is skewed. And is this ever going to be recognized? Now they recognize that there is the need for securing persistence of the tools and quality control and so forth. So and economizing on reusage of the tools between projects. Well, I think we've been 15 or 20 years ahead on that with Heelpix as an example. So anybody wants to look, you're welcome.
We shall emulate Heelpix, and I think that's a great place to end this one. I'm going to emulate Heelpix with some of my other software projects. So.
It takes a hell of a lot of enthusiasm of people participating, but well, we've been lucky to have it. So I really have to recognize my colleagues who are on the paper and some other ones.
Sure.
Without them, it wouldn't have happened, but I'm really glad we had that adventure.
Awesome. Kris, I want to thank you so much for sharing the story of Heelpix with us and walking through some of the technical details of it. It's been fantastic.
Thank you very much. It was my pleasure.
All right, everyone. We'll see ya. Bye-bye.
Bye.